Gnanam Paramam Dheyam. Knowledge is supreme.
Okay, so we have stated a primitive element theorem for finite separable extensions, and we will prove it now. So the theorem we will prove is this is primitive element theorem. So let L over K be a finite field extension, finite separable field extension. Then L over K is simple. This is what we want to prove. Proof. Let me just mention that this was the most important step in Galois theory. Galois was looking for a primitive element for a separable extension. In his time, all extensions considered were characteristic zero fields. They were characteristic zero fields, therefore all were separable, and they were all the time looking for primitive element, and that is very, very important step in the Galois theory. So let E over K be any algebraically closed field extension. Then what we have proved is, then since L over K is separable, we know that if n is the degree of the field extension, this degree is also equal to the separable degree L over Ks, and separable degree is by definition cardinality of the embeddings of L inside K, K embeddings of L inside K. So let us say that means these embeddings, there are precisely n embeddings. So let embedding set Le, this be exactly equal to sigma 1, sigma 2, sigma n. They are precisely n k embeddings of L into E. And what are we looking for? We are looking for an element Z. So we are looking for an element Z in L such that L equal to Kz, or equivalently this equality here will also follow from this inequality. L over K bigger equal to Kz over K, and this is equal to degree of mu zk. This is n, and this is bigger equal to, we have seen this degree is bigger equal to the zeros inside E, but sigma 1 z, sigma n z, they are all zeros of mu, because the sigmas are K-algebra homomorphisms, and this number. So this number is also n, because these sigmas are uniquely determined by Z on L. So therefore this number will be n. So therefore all these inequalities will be equalities, and we will get equality here, and we will get L equal to Kz. So I want to check that. So in other words, I want to find Z, in L such that the sigma 1z, sigma nz are all distinct. Elements of E. They are elements of K, but the distinct is important. So once we achieve this, then this number will be n, and this mu, they are all zeros of the minimal polynomial. Therefore the degree of the minimal polynomial will be bigger or equal to this. Degree of the minimal polynomial is the degree of Kz over K, and Z is contained in L. Therefore this degree is smaller or equal to degree of L over K, but this is precisely n. Therefore if I prove that these are distinct, then all will be equalities here, and this will follow. Clear? Therefore our problem is to find Z in L such that if I evaluate all embeddings of L into E at Z, the number should be different. There all these elements should be different elements of E. That is what we are looking for. So this will imply L equal to Kz, and we would finish our proof. Okay. So how do we achieve that? I should have said in the beginning itself, we may assume K is infinite, because if K is finite, and if L over K is a finite field extension of a finite field, then we already know that L cross is cyclic group, and therefore L will be simple extension. So that is not a big deal. So we are assuming K is infinite field, and we will proceed the proof. So therefore L is the finite extension of K. So L will generated by x1 to xn, not xn, xr, and by induction on R. Induction on R, enough to prove the case R equal to 2. So that means what? We may assume L equal to, L is generated by two elements. Now I will call them x and y, and I want to find an element z so that all values of different embeddings are different. So then for any indices I and j, I not equal to j but in between n and 1, these embeddings we know they are different. Therefore the values, these embeddings are uniquely determined by x and y, their values are x and y. If I know sigma x and sigma y, then that is uniquely determined, because this L is generated by x and y. So if I look at sigma I x comma sigma I y, this pair, this is a pair of elements in E, and we have the sigma j x and sigma j y. This is also pair in E. So if they are different, these are different, because if they are equal, each element of L is a combination of x and y, and therefore these two numbers will be equal, so that will be unique. So therefore for different I and j, these pair of elements are different. So this is, since sigma x, sigma y, this pair uniquely determines sigma I. All right. So now we have to each embedding we have a pair, and now we consider a polynomial. So consider the polynomial ft. This polynomial is product is running over pairs I comma j such that I is less than j, x is equal to n, sigma I x plus sigma I y t, this minus sigma j x plus sigma j y t, and then this is running over the product. This is like this. So you just stare at this polynomial. Obviously this polynomial f is non-zero first of all, because f0 means what? At least one of the element in the product will be 0. But if the element in the product is 0, that means this sigma x plus sigma I y t will be equal to sigma j x plus sigma j y t. But as a polynomial in t, therefore sigma I x will be sigma j x and sigma I y will be equal to sigma j y. But I is different from j, but that cannot happen because sigma I is different from sigma j. Therefore f is non-zero. Where are the coefficients of f? They are in Et. Coefficients of f are this. They are combinations of sigma I, sigma y and sigma j, sigma I. All are elements of E. Therefore, they are elements of T. E is algebraically closed. And we have a non-zero polynomial in algebraically closed field. Therefore, so in particular, it has finitely many zeros, and all the zeros are there. V, K, how many zeros are in? Now I look at the zeros of this in K, but this is contained in V, E, F, T, and this is finite. Therefore, this is also finite. It may or may not have a 0, but in any case it is a finite set. It may be empty set, but it is finite. Finite is important. Now it is a finite set, so I can find an element which is outside that. So therefore, there exists an element T in K such that f of t is non-zero, because since K is infinite field and a polynomial is non-zero, therefore it has 0, not all elements it is 0, so at least one element it is non-zero. And now let z equal to x plus yt. This is obviously an element in E, because t is in K, K is a subfield of E, and x and y are in L, and then therefore there is embedding, so they are in elements of E also. So these are the elements in, no, what I am saying is actually they are elements in L, because x is in L, y is in L, and t is in K, therefore they are elements in L. Now I want to check that this z is a required element. So we want to check that L equal to Kz, and that will finish our proof. All right. So look at sigma I of z. Sigma I of z is apply sigma to this, but sigma is a K algebra homomorphism. So this is sigma I x plus sigma I yt, but sigma I yt is same as sigma I y and sigma I t, but sigma is identity on K, therefore this is just T. Okay. On the other hand, okay, when I apply sigma jt, sigma j of z, what do I get? I get this is sigma jx plus sigma jy t. So I not equal to j. Okay, but now note that I is, if I is different from j, this cannot be equal to this, both these cannot be equal to, so I claim that this is not equal, because if it is equal, then if it is equal here, if equality, so I want to write by the other color, if equality here, then what happens? Then we get, look at this guy, sigma x plus sigma I y capital T, this minus sigma jx plus sigma jy capital T. This is one of the factor in f. This is a factor in f, and this factor will vanish at small t. That is the meaning of equality here. So this equality means the factor of ft vanishes at t, because equality here means when I evaluate at t, that is equal here, so it's equal here. But that will mean if a factor vanish, then f of t will be 0. But I have chosen f of t so that I have chosen t so that f of t is non-zero. So therefore this cannot be equal, and therefore sigma I z is not equal to sigma j z. So I have done. That means I have chosen my z. So this means for this z, sigma 1 z, sigma 2 z, etc., sigma n z are distinct elements of E, and that is what we wanted to prove. And this completes the proof. Now I want to indicate also that this proof we have done it by induction on the number of generators of L over K. L is a finite extension of K, and by the induction on the number of generators of L over K, we have proved that L over K is simple. But one can also avoid the induction and directly prove it. So I just want to indicate that direct proof. So this is remark. This is remark. One can do without induction as follows. So suppose L is a finite extension of K, therefore let us say L is generated by x0 to xm. And now instead of, we can consider the following polynomial. Consider the polynomial ft equal to product 1 less equal to I less than j less equal to n, and then the sum is from k equal to 0 to m sigma I xk t power k minus summation k is from 0 to m sigma j xk t power k, and do the same trick. So instead of do the same trick and use the fact that sigma and sigma j I will write in the next page, and use the fact that sigma I is uniquely determined by the tuple sigma I x0 sigma I xm, and the same trick. So I would just say here, complete the proof. Complete the proof. It's the same trick. No more extra trick is needed for this. So that was what. Now let us deduce some consequences from here. So the first important consequence. So corollary. Let L over K be a finite separable extension then F L over K, the set, this is the set of intermediary field extensions K contained in M contained in L. This set, so this is the definition of that set, then this is a finite set. That means there are only finitely many intermediary extensions. So proof. Since L over K is finite separable, L over K is finite separable, we know it is simple. L is Kx for some x by theorem. And we want to check that this is a finite set. We want to check this is finite. So I am going to give a map from this set to divisors of d mu xk. What is d mu xk? This is the set of monic divisors of mu xk in the polynomial ring in Kx. This is a monic polynomial, monic irreducible polynomial, not in Kx but in Lx. In Lx. It's a irreducible polynomial in Kx, but in L, when you go to L, it has a 0 in x. So it definitely this polynomial is not irreducible over Lx. So I look at the monic divisors of that polynomial in Lx. And what is the map? Map is very simple. Take any M, intermediary field, and look at the minimal polynomial of x over m. This minimal polynomial of x over m, and what is the relation between the minimal polynomial of x over k? This divides this where? In mx. But if it divides in mx, then it will also divide in Lx because L is bigger field. So our map is very simple, m going to the minimal polynomial of x over m, and I claim that this map is injective. So the map, we will check, we will prove that this map, what is the map? M going to mu xm is injective. What does that mean? How do I prove that map is injective? That means if I know this polynomial, then I should get back this m. So let us write this polynomial. Suppose this polynomial where this is a monic polynomial of some degree. So suppose it is x power m plus am minus 1, x power m minus 1, etc. plus a1x plus a0. This is the polynomial in mx. Then I say, then I want to prove m has to be equal to generated over k by these coefficients a0 to am minus 1. If I prove this, then injectivity will follow, because if I know the polynomial, I can get back my field. So I have to prove this equality. But to prove this equality, let us call this as m0, and obviously this is contained here because this polynomial has coefficients in m. So this is clear. So I have to prove the other way. So to prove the other way, I just have to compute this everything is a subfield of L. So I want to compute L over m, and also I want to compute L over m naught, and I want to show they are equal. If I show they are equal, then m will be equal to m0, because this is a subfield. Therefore this equal to L over m over times m over m0. This I know. So if I prove that this equal to this, then this m over m naught is 1 and m will be equal to m0. So I am aiming to prove these are equal. But okay, what is this? This is L is generated by x over k, therefore m is also generated by x over m. Therefore this equal the degree of this is a simple extension over m. So this is the degree of mu xm or mu xm. But mu xm, this is same thing as degree of mu x m0, because these two polynomials are same, because the coefficients are same. Therefore these two polynomials are same. These polynomials individually they are same. This polynomial and this polynomial are equal. Therefore their degrees are equal. And by the same argument, this equality. Therefore these are equal. Therefore from here you conclude m equal to m0, and therefore we conclude the map is injective. The map is injective. So if you want to give this name delta, the map delta is injective. So that proves that, so if you have an injective map from some set to a set where the bigger set is finite, this is a finite set because this is a monic polynomial of some degree, and therefore the number of divisors, monic divisors, will be also finitely many. Therefore we finish the proof, and next time we will continue therefore the consequences of this very important theorem. and we will also use this to compute some examples of some Galois groups. So thank you, and we will continue next time.